Zabiruddin Syed. I'm going to present a short paper on deep learning based face mask usage detection on low compute resource devices. This is the overview of the current presentation. The motivation of this project was that in the crucial periods of pandemics such as COVID-19, it is important that the social distancing protocol are maintained, and the face mask detection and classification aims to perform detection and tracking of crowds and perform analysis. The computer vision problems are challenging owing to different factors as shown in the slide. Now, deep learning has changed computer vision a lot and a lot of its application. However, deep learning requires heavy computational resources. The challenge in our work was the deployment of deep learning models on resource deficient platforms such as mobile phones or Raspberry Pi. But with visual data, there is excellent performance with the advent of convolutional neural networks which perform convolution operation instead of product operations that are there in dense layers. Different CNN architectures have been proposed ever since they have been planned for computer vision application. One of them was LeanIt, which incepted the concept of deep learning. It was previously used for handwritten zip code identification, and every convolution layer consisted of convolution, operation, pooling, and nonlinear activation function, which was tanh. Now, in the year 2002, there was a revolution in the form of AlexNet model, which was trained on ImageNet dataset consisting of millions of images. It consists of 5 convolution layers and 3 fully connected layers, and ReLU was introduced as an activation function. In 2014, VGG19 model, which was a deeper model with 19 convolution 3D layers, was proposed, and it was able to classify among 1,000 different categories of images. And ResNet was introduced in 2016, and it incepted the concept of residual connection. And there are no fully connected layers in this case, and this was a very deep network consisting of 152 layers. It overcame vanishing gradient problems, and there are no max pooling layers, no dropouts, and the basic design is based on VGG. The convolutions are mostly 3 by 3, and it utilizes batch normalization. Now, the Inception models, they brought the concept of network in network, and they connect the convolution layers through multi-layer perceptron that can learn nonlinear functions and eliminates the complete need of fully connected layers and employs global average pooling to spatially average the feature map in the last layer. Now, in the proposed methodology, these are the steps, starting with data acquisition, where we have used a real-world face mask dataset. We try to use the people of different age, background, diversity, and culture. There are 2165 images of people with mask and 1930 images of people without mask. Although the difference is very low, it is still an unbalanced data set. We have used data augmentation techniques like mirroring, random cropping, color shifting, and rotation in order to increase the number of images that we use in the training images. Now, the proposed face mask detection model, it is based on SSD Mobilenet V2 model. And the problem with the Mobilenet V2 model is that it overfits when compared to ResNet 50, V2, and Exception. Now, the architecture of Mobilenet V2, it consists of bottleneck blocks. There is a residual skip connection from the input block to the output block. There is an expansion layer and depth-wise separable convolution and the projection layer. In total, there are about 17 bottleneck blocks as shown in the diagram. And this is followed by max pooling layer, fully connected layers, and the softmax layer. Now, in our model, we have used regularization techniques to overcome the overfitting associated with Mobilenet V2. Transfer learning has been utilized to preload the weights from ImageNet dataset. The initial layers of the proposed model utilize the weights obtained after training on ImageNet dataset, and these weights are freezed, and the final connected layers are trained to obtain the optimal weights. It generates a classification model without the use of heavy computational resources. Now, this is the model summary of our face mask detection model. So until here we have the Mobilenet V2 architecture as basically a base model. On top of that, we are adding a head model which consists of global averaging pooling. Then we have like three layers which are fully connected, which has 128 neurons each for the first two layers, and in the last layer we have one neuron. And we have like dropout regularization added after every dense layer. And the dropout percentage in the head dense layer is around 50 percentage. And the final layer, it has only one neuron, and it classifies into two categories, that is a mask class or no mask class. Now in order to perform the face mask detection, we use the face detection model, which is based on VGG16 backend, and the base model in face mask detection is Mobilenet V2. And as I explained, we use the ReLU as activation in the hidden layers of head model, and in the final layer we have linear activation. So these are the stages of face mask detection modeling. So first we have the face detection or deployment phase, which is based on VGG16 model. So when we have like a Raspberry Pi camera, we have like image or video stream from which we gather the set of images or the video, and we load pre-trained VGG16 based face detection model. So that basically detects faces or the regions of interest from the images or video, and it is passed to the classifier that we have trained. Now the training of the classifier uses the base model of Mobilenet V2. It is initialized with weights from training on ImageNet dataset. We freeze the base model, we add the head model architecture, and in the head model architecture we add the regularization layers, and the model is trained using the face mask data sets. And the trained mask detection model performs the a mask detection on the images or the regions of interest which we have obtained in the deployment phase. Now the model implementation has been performed on a low compute environment, which is Raspberry Pi. It also uses Pi camera network, and the framework that we have used is TensorFlow, Keras, NumPy, OpenCV2, and Python. Now during the training, we have used a grid CV in order to like optimize the parameters, and the training phase parameters are finally being used is batch size of 32, number of epochs is 100, the learning rate initial was e to the power minus 3, and the training data instances was 3276. Now for the model evaluation, we basically use three metrics: accuracy, precision, and recall, and also F measure is used. Now the results of face mask detection. Now on the left hand side we have accuracy versus epoch, and on the right hand side we have loss versus epoch. And the red curve indicates the training accuracy, and the blue curve indicates the validation accuracy or the testing accuracy. The independent axis gives the epoch number, and the dependent axis represents the accuracy or loss. Now we see that the training accuracy and the testing accuracy, they converge after 20 epochs, and this indicates that our model is working correctly and there is no overfitting. So the disadvantage that we have for a Mobilenet V2 has been overcome in this case. And for loss versus epoch also, it represents the same way, that after 20 epochs the loss becomes very less and it is converged, and it stays the same when we increase the number of epochs. Now, results of face mask detection, the accuracy that has been obtained was around 100%, and there is no overfitting as it is shown by the previous graph. And if we see one of the images here, the detection of the face is also performed on the background. If we see here, and then also, like if someone wears a mask incorrectly, that is on the chin, we have identified or classified this as a no mask class with 100% confidence. And also for the face in the background, we have classified that as no mask with 100% confidence. So it shows that it is a highly accurate face mask detection model. Now, when coming to the conclusion, I would like to say that proposed deep learning Mobilenet V2 based framework has successfully classified people with and without face mask in real time with 100% confidence, and it can be used for crowd analysis framework because we have shown the results on the resource efficient camera platform of Raspberry Pi, and this can be easily integrated with surveillance cameras. and the overfitting has been avoided, and we gain effective performance without the use of GPU. The future work would involve that we would collect more data, including people belonging to diverse ethical and age profiles, and we also plan to train the proposed face mask detector with images containing people with transparent skin colored or prank mask types, which have become very prevalent nowadays. So these are our references, and I would like to thank you all for this golden opportunity to present my short paper on deep learning for face mask detection.